Okay, so yesterday we went over structure of the atom. We talked about, we ended off the day with Dalton's atomic theory. Okay, the 4 points of that, we'll review that today. We also talked about the Greek thinker who came up with the original idea of the atom. What was his name? Democritus. Okay, that's why I was inspired to have this meme up for today. Another great Greek thinker. Good enough, right? It's not really true. It's not really. Mediocrities is not a real person, but I thought it was funny. Because I have lots of dad jokes, and there'll be a different one up every day, because I'm lame that way. All right, so you can groan and roll your eyes. That's totally what I'm going for. Okay. All right, so Dalton's atomic theory. We were talking about this yesterday. We kind of ended off with this. Okay, the key points there, all matter is made of atoms. That's point number one. Okay, kind of shortened, but to the point. Okay, all matter is made of atoms. Okay, we talked about the indivisible part. Okay, it's true if we're talking about a chemical reaction. Okay, it's not true in its entirety. We know we can split atoms. Okay, we do it all the time. All right, point number two, okay, atoms of the same element are identical. Okay, so all atoms of carbon have 6 protons, and that's what gives them their physical properties. They have 6 electrons, okay, but there are that tiny amount of other ones called isotopes that may have a different number of neutrons, but it's still essentially true that all carbon atoms or all oxygen atoms are the same, and obviously atoms of different elements are different. That's what makes them different. Okay. Point number 3 was talking about what can happen when 2 atoms combine. Okay, if they combine, they form a compound, but they always combine in, we said this was the most important part, simple whole number ratios. So like 1 to 1, or 3 to 1, or 4 to 2, or whatever it happens to be. Okay, it's always going to be whole numbers. You're never going to have half of an atom in a compound. Okay, is that ringing a bell from yesterday? And then the last one, okay, we said that this one was the death blow to alchemy. You can't turn lead into gold. Okay, it says that in a chemical reaction, atoms can be separated. So that means a molecule or compound could be pulled apart. Okay, they could be joined, so 2 elements go together to form a compound, or they could be rearranged. Okay, so you could have a big long reaction like the one I wrote yesterday. Okay, I think I used this example yesterday. Okay, where I said HCl could react with NaOH, okay, and that would leave us with water and salt. Okay, did we make any new elements with that reaction? Okay, it's hydrogen, it's oxygen, it's sodium, it's chlorine on both sides. I didn't make any new elements. I can't turn lead into gold. Okay, that's where we ended off yesterday. Okay, Dalton's atomic theory. Should you be able to write those 4 points on your own? Yes. You don't have to write them word for word, okay? I'm not asking for a memorization here, okay? I'm asking you maybe write it down on a, like a cue card or something like that and go over that, okay, as part of your review for next week's quiz, because that's definitely something that would be on there, okay? All right, now, I think what I truly ended off with was the follow-up question to this theory. Okay, Dalton came up with this theory. It was pretty universally accepted by chemists, physicists. Okay, everyone was like, that makes really good sense. Okay, good job. But there was always a follow-up question. So what do atoms look like? Okay, to which Dalton would reply, didn't you read point number 1? I said they were really small. I can't see them. Neither can you. We can't use a magnifying glass. They're too small. I don't know what they look like. Okay? Which, is not a satisfying answer to people, right? They're like, well, you did all this work. Come on, you got to do better than that. Okay? So Dalton said, all right, what's a common shape? Okay, the sun is a sphere. The moon is a sphere. The Earth's a sphere. I'm just putting that out there. It's just not flat. It's round. Okay, and you got like all the other planets that you can see are a sphere. Sphere is a commonly occurring thing. Atoms are spheres. Okay, that was what he said. And at the time, there was nothing to say that that was wrong. We didn't know about the existence of protons, neutrons, electrons. We just figured out the atom. Okay, so a solid sphere made sense. Okay, so that was Dalton's model. Dalton came up with the solid sphere model and the atomic Okay, so if you want to just write down something quick for this slide, Dalton, solid sphere model, atoms are a ball. Okay. Now, as logical as that model was, it didn't last, okay? Because even when he came up with this model, people were already doing experiments in what we call electrochemistry. Okay, so these are chemical reactions that can produce electric currents and moving charges and things like that. Basically, the ancestors of the reactions that are used to power your phone, okay, or any other battery-operated device. Okay, these people were doing experiments on this, and a solid sphere doesn't explain where negative moving charges would come from. Okay, there's no part of this that's negative, okay, or that can move around or do anything like that. So these experiments in electrochemistry started to challenge this model. Okay, and eventually people are like, okay, this doesn't work anymore. We have to change our idea here. Okay, this just doesn't fit. So the person credited with discovering the electron, okay, J.J. Thomson, came up with a different model. Okay? Now, out of respect for Dalton, he kept the sphere part, okay, this solid sphere idea. Okay? All he said was, okay, the solid spherical part has a positive charge. And embedded on the surface of it, like just loosely kind of stuck to it, are these little negatively charged particles, which I will call electrons. Okay, because they appear to be where electricity comes from. Okay, so you could summarize this with something like this. J.J. Thomson discovered electrons and made the plum pudding model. Okay, that was what he called his model. Okay, so J.J. Thomson discovered electrons, okay, and made the plum pudding model. Okay, so why did J.J. Thomson say there's little negative charges stuck on the outside, but the rest of it's all positive? Okay, does that explain what we know today, or was that kind of just good enough for that time? Okay. There's some problems with having a big solidly charged or positively charged mass that little things are stuck to. Okay, it kind of explained that when electricity flows, there's no real change in mass. Okay, basically that electrons are tiny, okay, but positively charged things are big. It kind of explained that, but it didn't explain a lot of other behaviors that people in physics were starting to observe about matter. Okay, so as good as J.J. Thomson's model was when he came up with it, it didn't last very long. And in fact, there's a progression of models we are not even going to talk about, okay, that also had very short shelf lives because they just didn't kind of get accepted by everybody or explain behaviors that were discovered shortly thereafter. Okay, so we're kind of only talking about the main people, not everybody. Okay, so Thomson discovered electrons, comes up with the plum pudding model, okay, kind of explains how in a reaction the electrons could fall off and make an electric current, right? So in a reaction, maybe the atom gets shaken up a little bit, okay? The electrons fall off, okay, there you go, there's your electric current. Okay, but very shortly thereafter, okay, it was discovered that, no, there are actually positively charged particles. It's not a central solid mass, okay? So those positively charged particles were called protons, okay? Protons are way, way bigger than electrons.
Okay? And when we say like protons were discovered, it doesn't mean people observed them. Okay? We're still talking about incredibly small things. We still can't observe a proton. Okay? Like actually, you know, resolve it and see it. Okay? But they were able to kind of assume that they existed or infer that they existed. Okay? The problem with that discovery was they completely got their size and mass wrong. Because what particle is missing? We've covered the electron, we've covered the proton, what are we missing? The neutron. Okay? It's hard to infer the existence of something that has no charge in the time where this is going on, because you can't observe nothing. Okay? It has no charge, so it's hard to know that it's there. So they thought protons were way bigger than they actually were. And then when they started doing, you know, calculations and physical kind of computations and stuff, they're like, wait a minute, this doesn't really compute. This stuff is way too heavy. Okay? There's got to be something else there. And again, this is an inference. Nobody observed a neutron. They simply inferred. There's got to be something else contributing to the mass of these atoms. Okay? It can't just be protons. That would make them too big. Okay? So a lot of the attractive forces that work between positive and negative wouldn't work out if the proton was as big as they thought it was at that time. Okay? So that led to the discovery or inference of the existence of a neutron. Okay? It is exactly the same size and mass as a proton. It just doesn't have a charge. Okay, so from this slide, Chadwick, okay, discovered neutrons. Neutrons are neutral, and they're in, well, right now they don't know they're in the nucleus. We know they're in the nucleus. Okay, so what you're seeing here are two different schools of thought at this time for what an atom looks like. There's still the plum pudding-ish people that are like, okay, there's like this solid mass and the electrons, the protons, and the neutrons are all stuck on it, okay? And there's other people that are more of the nuclear family, okay, which is, okay, protons and neutrons sit together in the middle because they're the heaviest part, but electrons are really small, so they must circle because the attractive force between positive and negative could act like gravity holding the Earth in orbit around the sun or the moon in orbit around the Earth. It would naturally move in a circle. So you know, there were people that were along that school of thought, which is eventually, of course, the way we went. Okay, now, second to Dalton, Rutherford is probably the next most important person. Okay, so Ernest Rutherford, okay, is the person who proved the existence of the nucleus. Okay, so if you want to summarize what's on this slide right here, okay, we can say Rutherford proved the existence of the nucleus. Okay. And the other thing I would add, or the next sentence I would put on there would be using the gold foil experiment. Okay, we're going to talk about the gold foil experiment, okay, here in a minute, okay, gold foil. Okay, so Rutherford believed that there was a central dense nucleus that made up much of the atom. Okay, he thought most of the atom, and that electrons were kind of orbiting it on the outside. Okay, he was in that nuclear family, okay, of people who believed that in the existence of a central dense part of the atom. Okay, now he believed that that central dense part is where the protons and the neutrons resided. But he thought that atoms, the nucleus of an atom, was very small, while the volume of an atom might actually be quite large, but be mostly empty space. Okay, so he believed in a very small central dense nucleus. Okay, so what he said was, I'm going to run an experiment, and I'm going to have a very, very thin piece of gold foil. Okay, you've all handled like tin foil, aluminum foil, right, that you cook with before. Okay, imagine that, but made of gold. Okay, so an expensive piece of foil. You're not wrapping a potato and throwing it on the barbecue with this. Okay, but also much, much thinner. Okay, we're talking only a few atoms thick. So it would have been made of gold, but it would have had the consistency of like a Kleenex, okay, or a tissue. Like it would have been really flimsy, really thin, right? And what he was going to do is he was basically going to take an X-ray machine, okay, and fire what we call alpha particles at this piece of gold foil. Now, what he thought would happen, because atoms are mostly empty spaces, he thought the electron or the X-rays would go right through. Okay? Because there would be so much space between the atoms, so much empty space, that the X-rays would go right through, and he would be able to get like an exposure on the far side of the foil. Okay, so his experiment looked like this. Okay, now this is going to be a bit of a generation gap thing, but you've probably heard that cameras used to have this stuff in them called film. Okay, guys, you know what I'm talking about? And the cameras haven't always been part of your phone and digital. Okay, they used to have this stuff called film, and all that would happen is if you exposed the film to light, it would just go from being brown to being kind of white. Okay, if you have a camera that flashes a shutter open really quickly, that exposure is short and it captures an image. An X-ray works the same. Okay, if you're getting an X-ray, you know, at the hospital, you know, you put your arm up against that thing and they shoot the X-ray at it, and the film's behind it. Okay, your bones, okay, reflect, or the X-rays don't go through your bones, but they do go through your flesh. Okay, so what you see there is the part that actually reflected the X-rays. So he thought what was going to happen was all of this back here was just going to turn white. Okay, because the X-rays were just going to go through the spaces between the atoms. But what actually happened was, yes, he got an exposure back here, quite a few particles made it back here, but he got exposures almost everywhere, even some almost right back where his emitter was. Okay, which to him was shocking. Okay, he did not expect atoms basically to be as big as his experiment proved them to be. Okay, so essentially what happened was, okay, he had, you know, the 4 atoms thick piece of gold. Okay, and most of the X-rays went between the nuclei. It didn't hit anything, so they just passed right through. Okay, but some of them would hit the nucleus of an atom and they would be deflected. Okay, you know, like when you play pool, right? You hit a ball, you hit another ball, and they kind of go separate ways. Okay, so a lot of those X-rays just bounced right off, and that is what caused the other exposures that he observed on the film. Okay, from the angle of those exposures and the number of them, he was actually able to calculate how big the nucleus of a gold atom was. From there, able to calculate essentially how big a neutron and a proton would be. Okay? It was like a crucial experiment in proving the model, or that an atom has a nucleus. Okay? Crucial experiment for doing that. All right, so if you can have some sort of little blurb about his gold foil experiment, okay, that the rays got deflected, okay, something like that, okay, that's essentially what you need to know about Rutherford. Prove the existence of the nucleus using the gold foil experiment where alpha particles were deflected. And he actually was quoted as saying it was like firing an artillery shell at a piece of tissue paper and having it bounce back at you. Okay, which would have been kind of an exaggeration, but that's kind of how he described it. Okay, now, common theme that we've kind of been covering here is every time somebody does something really good, they're immediately like, yeah, but, okay, like the rest of the scientific community is like, yeah, but, Okay, so like, Dalton comes up with the atomic theory, and everyone's like, yeah, but what do they look like? Okay, Thomson comes up with the plum pudding model, and people are like, yeah, but why is that all positive? And so on and so on. Well, there was a yeah, but for Rutherford as well. Okay, everyone's like, great, you proved the existence of the nucleus, but what are the electrons doing? Your experiment doesn't say anything about what electrons are doing, where they are. Okay. And Rutherford's like, man, you guys are really hard to please. Okay? And so what he said was, well, they orbit the nucleus. The rest of the models we're going to talk about are all, yes, there's a nucleus, but what are the electrons doing? Because everybody disagreed, okay, on what the electrons must be doing. Rutherford said that they basically, oh, sorry, that's the Bohr model. Go back one here. This is what Rutherford said they were doing. They were all in concentric circles. Every electron was the same distance from the nucleus, and they just orbited in a circle. Those circles were just offset by a couple of degrees. Okay? That fell apart real fast. Okay? Because it works fine if you're talking about smaller elements that might only have, 10, 15, maybe even 20 electrons. There's enough room for all of that. But when you start getting to a big atom, okay, that has, 80 or 100 electrons, you start running out of room for all of those circles to not overlap. Plus, electrons are all negative. What do like charges do to each other? If you try and put two negatives together, they're going to push apart. They'll repel. Well, if you start trying to cram a whole bunch of electrons into the same space, they're going to start to push each other away, and that's going to cause a breakdown in how an element or an atom would function. So his model, even though the nucleus part is the important part of the experiment, okay, the part about the electrons was completely wrong. Okay? So he actually worked with another scientist named Bohr, who came up with the planetary model that kind of accounted for, you can't put them all the same distance. So they're like planets around the sun. Some electrons are really close. Some electrons are a little further away. Some are a little further away than that, and so on and so on. Okay? And that model was pretty widely accepted, even like during World War II when they were developing the atom bomb. People were still mostly like, yeah, that's probably how it works. Not that it was important to developing the atom bomb at all. Okay? So the Bohr model, okay, basically says, yep, electrons can sit in these orbits. The closer the orbit is, the fewer the electrons in that orbit. Okay? The further away they get, the more electrons can be in there because there's more space and they won't repel each other as much. Okay? For the most part, people were pretty happy with that. Until, okay, you don't need to worry too much about Bohr, okay, because his model is okay if you take a picture of an atom, if you could. If you took a picture of an atom and the electrons were frozen in time, that's probably what they would look like. The problem is that an atom is dynamic. It's always changing. And electrons don't just go around and around. Okay? What was discovered after this is that atoms don't just orbit, they can jump vertically. Okay? And they jump vertically based on how much energy they have. Okay? It's kind of like if you're like whirling something around and around on a string, okay? If the circle is really small and you're whirling it really fast, you have to hold on really tight, okay? But if you let it go further away, it doesn't have to move as fast and you don't have to hold on as tight, okay? But if an electron gets going fast, it can only stay in a small circle for so long before it's going to want to jump to a bigger circle, okay? We call that a quantum leap, okay? And electrons do it all the time. In fact, it's how photosynthesis works. Okay? In chlorophyll, when light hits it, the electrons gain energy and they move faster and faster until they can't be held in a certain orbit. And then they jump. They make a quantum leap to a higher level. And they'll continue to jump to higher and higher levels as long as the sunshine is present. Then, when the sun goes down or goes behind a cloud, there's nothing to hold them out there to keep having them with that kind of energy and speed, and they fall back. And when they fall back, they give off the energy they absorbed. That's the energy that makes the sugar. Okay? It's electrons falling back towards the nucleus that gives the plant the energy to take carbon dioxide and water and turn them into glucose in photosynthesis. Okay? So it's actually plants that led to our discovery of how electrons move about in an atom. Okay, so that is kind of our last model, okay, and that is the de Broglie model, and we call it the electron cloud. Okay, and then I would say probably this sentence here would also be worth writing. So what's the end result of all of this for you, okay? Yeah, you're gonna need to know a little bit of the trivia that we've gone over, the who, the what, okay? So, you know, that Thomson discovered electrons and made plum pudding, okay? That Dalton came up with the 4 points of the atomic theory in the solid sphere, okay? And know those 4 points. Know Rutherford did a gold foil experiment, okay? You know, and prove the existence of the nucleus. Know that de Broglie has the model we currently accept, the electron cloud model. Okay, yeah, you're gonna need to know that trivia for sure. The other thing you're gonna need to be able to do is, I will, on both a quiz and your unit exam, ask you to draw a picture of a specific element's atom. Okay, that means I would want to see protons with the right number of protons, the right number of neutrons, the right number of electrons, and all of them in the right place in a picture of an electron cloud. Okay, so what's that gonna look like? Let's say I ask you to draw a picture of a nitrogen atom. Okay, how many protons does nitrogen have? Oh, 7. Okay, the atomic number, that tells you the number of protons, so you can always use that to know the number of protons. It's also the number of, not always, close, but not always, electrons, okay, because an atom is electrically neutral, so those two always have to be equal. So that atomic number tells you there's this many protons and this many electrons. You have to calculate the number of neutrons. You use that number, okay, you use the atomic number, and you use the atomic mass, this number. Okay, did I forget to give you guys your periodic tables? I did. Let's do that, because you're gonna need those. Okay, so for nitrogen, okay, we know that it's going to have 7 protons, we know it's going to have 7 neutrons, and we can calculate how many neutrons, okay? The way we calculate the number of neutrons, we take the atomic mass and we subtract the atomic number. So on this particular one, it is actually 7 as well, okay? It's not always that, but sometimes it's, you know, enough, it's slightly more, okay? So, for an atom of nitrogen, okay, we would have, okay, 7 protons in the nucleus and 7 neutrons in the nucleus. So, I would say, you know, do something like this. Say like positive equals protons, okay? Maybe just a blank circle can be a neutron, okay? And maybe, you know, like a negative sign can be an electron. All right, so okay, so there's 14 particles, so I'll just kind of randomly pick. Okay, so now I've got 7 protons. I've got 7 neutrons. They're all stuck together, okay, in a nucleus. And then I need 7 electrons in a cloud. Okay? That would be a 5-mark question. Okay? I would give you 1 mark for having 7 protons. I would give you 1 mark for having 7 neutrons. 1 mark for 7 electrons. 1 mark for having everything in the right place. So that would be the protons and neutrons in a nucleus and a cloud containing the electrons. Okay, and then that would also be another mark for having the right model. That would be de Broglie's electron cloud model. Okay, 5 marks. Pretty easy 5 marks, especially since I'm telling you I'm absolutely 100% going to do this. Okay. All right, so is that terribly difficult? Probably the trickiest part of that is calculating the number of neutrons. Just have to remember atomic mass minus atomic number. So maybe we'll put that on here. Okay, so atomic mass minus atomic number equals the number of neutrons. Okay, so this is what we just talked about. We just drew one of these. An atom, believe it or not, is mostly empty space. That's what Rutherford proved. Okay, the nucleus is central and it is dense. Okay, and the electrons occupy a great deal of space. Okay, surrounding it. Okay. All right, so there. This is something you learn kind of first day of Chem 20, but there's actually locations where the probability of encountering an electron is higher than in others, especially based on its energy. It's not something we need to know for Science 10, okay? Yeah, we've talked about all of that stuff. Actually, we talked about this yesterday here, okay? Which is that the number of protons is what influences the physical properties of an element. So if you don't have that in your notes somewhere, okay, it is the number of protons, okay, that determines the properties of an element. Okay, questions there? All right, how many people were able to print the workbook for chemistry? Okay, over the weekends, okay, I would highly advise if you are able to have a paper copy of that so that you've got, access to it when we're doing seat work, okay? But the first page in that workbook, eventually, okay, has 12 questions on it, I believe, okay? And they are all related to what we've covered yesterday and today, all right? So, rest of class, I want you working on these, okay? You probably won't get them done, but I would like to go over these at the start of Tuesday's class, okay? So, I'm not checking whether you have these done at the start of Tuesday's class, but it would be a good idea for you to have these done for the start of Tuesday's class, all right? So, I'll put them up here, okay, I'll scroll up, okay, in a few minutes I'll move up, okay, and we can work on them.